Problem is from GATE 2017 Mathematics paper, question number 27. The problem given is, given two n cross n matrices A and B with entries in C. C is complex plane. Consider the following two statements. Statement P. If A and B have same minimal polynomial, then A is similar to B. And statement Q is, if A has n distinct eigenvalues, then there exists a vector u in C power of n such that u, au, and so on, a to the power of n minus 1 u are linearly independent. So then it is asked that which of the above statements holds true. Option A, both P and Q. Option B, only P. Option C, only Q. Option D, neither P or Q. So it is given two statements P and Q related to two matrices A and B with entries in complex plane. Then it is asked that which of the statement is true. So let me start the solution. So it is given that A and B are two n cross n matrices with entries in C. So let's consider the first statement, that it is given if A and B have same minimal polynomial, then A is similar to B. So to prove a statement, if it is correct, if to prove a true statement, we have to find some solution to prove that statement. But to contradict a statement, if we can find one example saying which contradict that statement, so we can state that statement is false. So similar to this, for the statement P here, if we can find one example which contradicts that statement, so we can say that statement P is false. So in particular, so it is given that if A and B have same minimal polynomial, then A is similar to B. So whenever we see a statement, to find whether it is correct or wrong, so if we are not in a situation to prove that statement, so it is better to find an example which contradicts this statement. So suppose this statement is not true here, so then can we find some examples which contradicts this statement? Yes, we can find for this statement. So it is given that two matrices A and B which have same minimal polynomial, then A is similar to B. So we have to find an example in such a way that A and B have same minimal polynomial, but A is not similar to B. If we can find an example in that way, we can say then this statement P is wrong. So for that kind of example, so I'm considering the matrices A and B as the following matrices: 1 1 0 0 0 1 0 0 0 0 0 0, sorry, here 1, 0 0 1, sorry, 0 1. So why I am considering only this matrix? Okay, let me write B also, then you can understand. So 1 1 0 0 0 1 0 0 0 0 1 1 0 0 0 1. So if you observe these two matrices, we can find one thing, that the first two rows of these two matrices are same, whereas coming to the third and fourth row, this fourth row is also same, but coming to the third row, it is different. So why I am considering like this only? If you observe the matrix A, you can see that there exists a block. In fact, these two matrices are nothing but the Jordan blocks are in Jordan canonical form. So if you observe the matrix A, you can see there exists a 2 cross 2 Jordan block corresponding to the eigenvalue 1. And whereas coming to the matrix B, there exist two Jordan blocks, each of order 2. corresponding to the matrix B. So you can say the minimal polynomial for A and B is nothing but x minus 1 whole square, because 1 is the eigenvalue and each matrix has a Jordan block of order 2. So that is why the power is coming 2. So what is the highest order of the Jordan block corresponding to the eigenvalue that comes as the power corresponding to that eigenvalue. And of course, here you can see 1 and 1. These two are of order, these two Jordan blocks of order 1. But we have the highest block of order 2. So that highest power, highest order will come in this power. But you can observe here that these two matrices are not similar. But A and B are not similar. And the reason why these two matrices are not similar is left to the reader to observe why it is. So you find why these two matrices are not similar. So now coming to the statement P, so we can so from this we can say statement P is wrong. Now coming to the statement Q, it is given that if A has n distinct eigenvalues, then there exists a vector u in C power of n such that the vectors u, au and so on up to a power of n minus 1 u are linearly independent. So again we find, so given statement is if A has n distinct eigenvalues, then there exist u in C power of n such that u, au and so on a to the power of n minus 1 u are linearly independent. So we prove this statement in contradiction method. I mean, we prove or disprove the statement in contradiction method. So suppose this statement is false. Suppose Q is not true. So what does this means is, so when we have the matrix A with n distinct eigenvalues, then we can always find, so it is given that here there exist u such that these are linearly independent. But when the statement is not true, it means that then for all the vectors u in C power of n, these vectors u, au and up to a power of n minus 1 u are not linearly independent for all such kind of u's. That is, for all u in C power of n, the vectors u, au and so on a power of n minus 1 u are not linearly independent. That means linearly dependent. So since A has n distinct eigenvalues, so it will have n distinct eigenvectors also. It has n distinct eigenvectors. So let those be v1, v2 and so on vn are the eigenvectors. So that means, okay, eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, so on lambda n. So we have n distinct eigenvalues and eigenvectors. So and by the assumption of by the supposition of the statement is not true. So we have for all u in C power of n, we have these are not linearly independent. So if we consider this statement, what happens? So let's see. In particular, consider u as, so by the supposition we have for all u in C power of n, we have this is linearly dependent. So in particular, we consider the vector u as v1 plus v2 plus and so on plus vn. Since all are distinct here, v1 v2 up to vn, so let's consider this as u, which is in C power of n. So then what happens? Consider then for u there exist scalars, namely let me say a1 a2 upon an, not all zeros, such that a1 v plus a2 av plus an e to the power of n minus 1 v equal to 0. Since by supposition we have for all u these vectors are linearly dependent and we consider this u as this. So since these vectors are not linearly independent, so there exist scalars of this kind a1 a2 up to an such that this linear combination is 0. So from this, can we see any contradiction or not? Let's see that. So we have a1v, a1 times v is nothing but u1 plus u2 plus and so on plus un plus a2 times a, v is again u1 plus u2 plus and so on un plus and so on plus an times a to the power of n minus 1 times u1 plus u2 plus and so on plus un equal to 0. So what does this mean? We have a1 u1 plus a2 u2 plus on so on an un plus a2 times we have here a u1, that is nothing but since we have u1 is the eigenvector, so eigenvectors corresponding to the matrix A corresponding to the eigenvalue lambda 1. So we have this as lambda 1 u1 plus a2 lambda 2 u2 plus and so on a2 lambda n un plus and so on plus here we have already u1 is again the eigenvector corresponding to the matrix A. So we can say a to the power of n minus 1 u, that is nothing but lambda power of lambda 1 power of n minus 1 times u, and of course we have an plus an lambda 2 power of n minus 1 u2 plus and so on an times lambda power of lambda n to the power of n minus 1 un that equal to 0. So from this we observe that if you take u1 common, so we see a1 plus a2 lambda 1 plus and so on plus an lambda power of n minus 1 plus u2 times similar kind of combination a1 plus a2 times lambda 2 plus and so on plus an times lambda power of here lambda, here we have u1 and so hence we have lambda 1 power of n minus 1 and similarly here we have lambda 2 to the power of n minus 1 plus and so on plus un times a1 plus a2 lambda n plus and so on plus an times lambda n power of n minus 1 equal to 0. So what does this equation represent? So we have a1 a2 and so on, an are scalars and lambda 1 lambda 2 up to lambda 1 power of n minus 1 These are also scalars. So in total we can see this entire expression is scalar, and again this is scalar, this is scalar. So that means a linear combination with n different scalars with the linearly independent vectors. Since u1, u2 up to un are eigenvector corresponding to the matrix A, which are linearly independent. So this represents a linear combination with the linearly independent vectors u1, u2 up to un. So what can we say from this? Since u1, u2 up to un are linearly independent, so the linear combination with which is making 0 to these vectors has to be zeros. That means the scalars has to be zeros. That is, the scalars are nothing but a1 plus a2 lambda plus and so on a1 a2 lambda 1 plus and so on plus an lambda 1 power of n minus 1 equal to 0. And similarly a1 plus a2 lambda 2 plus and so on plus an lambda 2 to the power of n minus 1 equal to 0. Similarly a1 plus a2 lambda n plus and so on plus an lambda n to the power of n minus 1 equal to 0. And one thing we should observe here, that we have all the eigenvalues lambda 1, lambda 2 to lambda n are distinct. So when we write this in terms of matrix representation, we can see that this can be written as 1 lambda 1 and so on lambda 1 power of n minus 1, 1 lambda 2 and so on lambda 2 to the power of n minus 1, 1 so on lambda n and so on lambda n to the power of n minus 1 times a1, a2 and so on an. This is equal to 0. And here since we have lambda 1, lambda 2 and so on lambda n are distinct eigenvalues with of the matrix A, so we can see this, the determinant of this matrix is non-zero. Since, so let me write this as mx equal to 0. Since lambda 1, lambda 2 and so on lambda n are eigenvalues of A, we have the determinant of m is non-zero. That means we can find, that means the solutions of this system of equations are nothing but this vector a1, a2, an. This has to be 0 only. That implies the vector a1, a2 and so on an has to be 0 only. Since this matrix is non-singular, if we multiply both sides with its inverse m inverse, we can see this becomes I times this vector, that is nothing but this vector again, which is 0. So but it is a contradiction to our statement that for all u there exist scalars not all zeros, such that this is 0. But since we, by the assumption we have these are non all zeros, but which we have derived is all these scalars are zeros. So we can say the statement, sorry, our assumption is wrong. So the statement which we has assumed that the statement is true, not true. So our statement has to be true. So statement Q is true. That is, when we assume, we suppose the statement is not true, we get a contradiction. So we have the statement Q is true. So that statement P is not true, Q is true. That is, only Q is true. Answer is option C.